First time I did the stream live on YouTube, I thought was a big thing. Now I do it every class, so change of perspective. Okay, let's do the resume share. We are back. Okay, very good. Welcome everyone. Today we are first doing a class on the new topic, which is planning. And then we have a short break. And then we do the exercises that were given last week, which will cover essentially search, okay? I think there is a slide, so let's not anticipate. We are jumping at chapter 10 of the book. And I think that the order of the new version is the same. Why do we jump to chapter 10? Well, the reason is the following, that the book decided, the authors of the book decided to deliver the section on knowledge representation and logic before planning, which is a reasonable choice because one way of formalizing planning is by considering states of the problem represented as logical formula. But in fact, we are looking at a version of planning called classical planning, where this is not really needed. And therefore, I prefer to grow from the less structured representation, which is the one that we have seen until now, except for constraint satisfaction, which is already a factor representation, and then go from the less structured model to the more structured model. And planning in the classical form represents states in a relatively simple way, because it's essentially using a set of Boolean variables. Okay? And they can be seen as a conjunctive formula, but we don't need to have this logical reading. Okay? So that's why I jump to chapter 10. We do planning, and then we do logic later on. Okay? It's a choice. I prefer this way. So you have to be a little bit adaptable in reading the book at this stage, because sometimes in the book you find formula. Okay, I will explain later how this formula should be interpreted. Okay, there isn't much else in terms of logics in this chapter, which shows that it could have been anticipated as we're doing. Okay, that's the first thing I wanted to say. Now, yes, the overhead projector. Of course, there is always something missing. Well, as a remark to the teacher, is a little slow, because I am already at slide 3. Okay, here we are. This will require a little restructuring of the screen here. Okay. Okay. So here is one example which is intended to show that the number of options that are available when we do search can be very large, and having the appropriate heuristics may not be easy. So here is one example. Consider a task of buying milk, bananas, and a cordless drill, which apparently is quite easy. Consider the number of options of buying objects. Consider the number of options of going to stores. This is going to be a very large branching factor, okay? And search, although guided by heuristics, can often be ineffective on problems where the branching factor becomes so large. In fact, one of the features that we will see for planning is the ability to handle parameters. Okay? Now, oops. Next. Okay. The even more detailed comparison between search and planning is reported in this slide. This is a question that, you know, that the exam, it's made of exercises and open questions. One of my favorite open questions is what are the differences between search and planning? They both do search, right? The key difference is that while in search, the representation is built ad hoc with ad hoc data structures. Here they say Lisp because, you know, Lisp is the language for AI. It used to be, okay? While in this case, in the case of planning, we have fluence. We'll see in a moment, but I anticipated that they are nothing else but a set of Boolean variables, okay? Then actions are coded, essentially, while in planning, actions are specified by defining preconditions and effects of each action. So for example, if you introduce a new capability, we have to introduce a new action, and it's just change of the action description, or add the action description rather, and everything else will be untouched. So a factor representation can scale up with, you know, or keep, support reuse. Maybe that's another way of saying it. When the problem changes. The goal, we know that either a goal is in search is explicitly given as one or more states, otherwise it's given through a function, which is true whenever its argument, a state, corresponds to one of the goals. So for example, in chess, it's mate. Mate is not a set of positions predefined. It's a function that needs to be checked on the board. While in this case, we're going again, a representation which is in terms of a set of states, but in fact, we are going to see this representation as a set of fluents in a moment. And then the plan is just a sequence, and we will see that in planning, we also will extend the notion of a plan. We're not going to rely simply on the straight sequence of actions, okay? So these are the big changes. And given these changes, the important thing is that we are no longer using heuristics in order to have efficient algorithms, because the heuristics, like in constraint satisfaction problem, will be domain independent, okay? And that's very powerful because it allows to scale up with problems without, say, knowing the solution. Remember that what I sometimes call the perfect heuristics amounts to knowing the solution, which is knowing what is the right choice for the next expansion in the state space. okay? Okay. Oops. So much for the introduction. Now, in terms of our agent, we again have a planning agent. Remember that the initial characterization of our agents, we are not talking about learning agents, which is the topic of the parallel course taught by Professor Iocchi. Here we are talking essentially about planning agents, and in which setting. The restriction on the setting initially are quite strong. Some of them will be removed. Some of them will remain. So we are talking about a world which is fully observable, deterministic, static, and discrete. Besides being discrete, typically it's also finite. Recall what this means. Fully observable means that the agent knows everything, okay, about the environment. Deterministic means that the effect of each action is guaranteed. And static means that while the agent is thinking, nothing happens. The world doesn't change except for the action of the agent, which is a strong assumption. And then it's discrete. We're not talking about the continuous domain. And as a consequence, a plan is going to be a sequence of actions. Everything in planning dates back to a language called STRIPS, which stands for Stanford Research Institute Problem Solver. And actually, I think that this goes back to the 70s. It's the Stanford Research Institute, SRI, is the institute where I spent my sabbatical in the US. Well, sabbatical at that time was just part of my education because it was very, very long ago. And they had the first robotic project where they wanted to show that the actions of a robot could be driven by high-level symbolic reasoning. And therefore, to this end, they devised this planning language, okay? Later on, things have evolved, and especially for the robots, we now understand that it's necessary to take into account also uncertainty in many circumstances. But for example, the sequence of steps to be taken on a map in order to go from one city to another city or from one location to another location is a plan, okay, high-level plan. So, for example, for robots, one of the approaches that we have pursued in our research is to use classic plans, or classic planning, as we call it now, and then have uncertainty which is introduced at the level of action execution, okay? So there is a mixture of ways of dealing with uncertainty. Okay, let's introduce some terminology. I mentioned that we call these elements that characterize the states, we call them fluents. These terms derives from a specific logical formalism called situation calculus. I don't think we even mentioned this, but I think it's, so maybe they are not everywhere in every book called fluents, but in fact it's, what are they? If we look at them from a logical point of view, they will be atoms in logical language, or better literals, because they can be positive or negative. In our case, we simply say that what is a fluent? It's a predicate that can have some arguments. And the arguments can be either variables or constants, okay? And these fluents can appear positive or negative. with a not negation sign in front of them. And they take a Boolean value. Either they're true or they're false. So states for our problem will be represented by sets of instantiated fluents. What does it mean? That generally speaking, we will find, especially in the action description, that sometimes we have these predicates with variables. But when we consider the states of the system, we are considering only the instantiations. Okay? We'll see in a second some examples that will clarify this. One important point in this representation is the so-called closed word assumption. The closed word assumption is not applied only in planning, and essentially corresponds to the fact that in order to characterize a state with this representation, we only specify the positive fluents. And we assume that every fluent that is not positive will be negative. Okay? So this is typically the case, for example, also in databases. If you take a relation in a database, it's telling you the actual instance of the relation. And typically, everything that's not in the table is assumed to be false. Take a table with flights. If you have a table with all the flights, if a flight is not on the table, that means that there is no such flight. Okay? And the same is here for the state representation. Then, of course, I already mentioned there is a relation with logic because a state can actually be represented through a logical formula, and the representation can become much more compact with the logical formula in certain cases. And the other thing that we want to specify explicitly is that we make typically an assumption that the domain, which the domain is, domains are finite. What is a domain? It's where the variables take their value. Okay? So if we talk about people and we have a fluent person, then the number of instances will be finite in our set, okay? Now, maybe person is not the proper, we'll see other fluents in a second. A person doesn't change, right? So fluents are typically property of the state that change. If we say a live person, then we have a state change. And that can be a fluent, but person itself is not a good example. Okay, so fluents are typically used in order to characterize properties that change over time, even though time is not mentioned here. Questions as we go? Questions from the class? Silence. Well, we are here being recorded, but in the second part of the class, I will ask questions to you. Okay, so here is an example. Initial state, we want to say that, for example, our agent in the initial state is at home. At is a fluent because if in our domain there is an action go, this will change the state of at, right? Because at is representing the fact that in a certain state, the agent is at home. In this particular case, this is the initial state. I'm not insisting particularly on the notion of initial state and goal because you already know from search. And at the same time, in the initial state, we have that the supermarket is selling milk, that it's selling also bananas, and that the hardware store is selling the drill, and so on and so forth. Okay? Everything should be specified. And suppose that for the supermarket, there are no other instances of objects that are sold in the supermarket. We are going to be describing a very funny supermarket, which is selling only milk and bananas. Because everything else, if there are other objects, they are not sold at the supermarket. Okay, that's the closed word assumption on this initial state. If something is mentioned explicitly, it's true. If it's not mentioned, it's false. Okay? So in the state, we don't use negation because it's always be implicit. This is telling also something else to us, which is everything is specified in the state. Because if it is not true, then it's going to be false. There is no uncertainty. Things have to be either true or false, which is some restriction that we'll eventually remove at this later point. So we know that this is a factored representation because every problem will be characterized as a set of fluents. And we know that there are algorithms that are independent from the specific problem will be devised in order to reason efficiently on this representation. Okay, so we have an initial state, we have a set of goal states. Then the key element of our representation are the so-called action schema. Schema because we are introducing here the variables. Otherwise, fluents will be always instantiated. But if we want to say that we have an action to go from one location to another location, we have to have parameters. The two locations should be unspecified beforehand. Otherwise, we would have to provide all the possible moves in advance. And we don't want to do it. We have variables in order to do that. Okay? And action schemas have their variables. They appear both in the preconditions, which is a set of fluents, and in the effects, which again is a set of fluents. Okay, so we reason in terms of these Boolean variables. Now, as we said, if we have variables, they have to be instantiable in a finite number of individuals. And we can have more general representation in logic formulae. You don't, well, it's below here in the screen. I'm sure at home, they see the screen. So, oh, I see what's the problem. That I share the screen after I connected the projector. So the setting of the screen changed when Well, this line is not so important because it's, we'll keep it as it is for the time being. We'll see if we really need, I will restart the whole thing, okay? Be patient. Anyway, in this line, we say that in the book, you will find that instead of commas, which separate the elements in the set of fluents, there will be conjunction signs, where a conjunction is written as like this, okay? Okay, let's see. Okay, there is an example of action schema for our supermarket domain. We want to define the action buy. It's an ideal action buy because as a precondition, it requires only that the agent is at a location P, where P is a variable, namely a parameter. X is a parameter of the action, and P is a parameter of the fluent at. And then we have to have that the item P is sold at X, where X is another variable, which will indicate one of the possible objects that can be instantiated to shops. Okay, remember that we had the supermarket and the hardware store in our example. So supermarket will be a reasonable instantiation here. Now, why is this an ideal precondition? Come on, someone.
There is no interaction with nobody.
No, that's not it. Well, close, because there is not a price. Actually, this agent could buy anything in the supermarket without money. Right? Having money in order to buy the item is not a precondition. So in that sense, it's an idealistic representation, okay? In other words, if we don't model this explicitly, we are assuming that in our problem, our agent always has money to buy stuff, okay? And here is another representation, graphical representation that I don't think we are going to use very often because it was used in the earlier versions of the book, but it's still there. So we have the precondition on top of a box, which gives the name of the action, and on the bottom of the box, we have the effects. Now, Fx is the effect of this action, and essentially, the action will be executable, we'll see in detail a definition, but will be executable in a state where the agent is at the location where the item is sold. And the effect of the action is that after the execution of the action, the agent will have the object or the item both. Okay? Let's see in detail. Here is the definition of a precondition. An action A with preconditions Q is applicable in a state if every positive fluent in Q is also in S, and every negative fluent in Q is not in S. So in the precondition, we can have positive and negative fluents. The state is represented only with positive fluents. So if we want to apply an action, we have to make sure that the positive fluents are in the state and then the negative fluents are not in the state, fluent of the precondition, okay? There is another important thing to mention, that for an action to be applicable, it must be the case that all the variables in the preconditions are instantiated, which means that the effects, the variables in the effects will be instantiated as well. The important thing is that they will be instantiated, the variable in the effects, because they have to specify a state. Okay. Of course, if there are no negative fluents in the precondition, it's just set containment, the check of the precondition, right? Okay, now we have to provide, we have explained when an execution, an action is executable. Now we have to specify what is going to be the state after the execution of the action. We know that we have, in the action specification, we have effects. And these effects can be positive fluence and negative fluence. So for the positive fluence, what happens is that they have to be true in the state. So they have to be added to the state. While for the negative fluence, they have to be false in the state, which means that they have to be removed from the state representation. In order to highlight this add and remove operation, it's, the effects were also represented originally in strips as the add list and the delete list, which correspond to the positive literals in the fluent and the negative literals in the fluent, because the first ones, they have to be added, and the latter have to be removed. Another key point in this representation is that strips, and therefore classic planning, they adopt a very strong assumption with respect to all the other fluents. What happens to all the other fluents that are not in the add list and in the delete list? They are unchanged. In other words, the action is going to change the state only concerning the fluents that are explicitly mentioned in the add list and in the delete list, or that they are explicitly mentioned in the effects, either positive or negative. Okay? We will see that this is not the case in logic, but this is something that we will see when we will talk about logic. For the time being, we note that in this model, we specify in the action effects only the fluents that change. Okay, they can change from true to false, and they can change from false to true. What have I done? Maybe if I do it now, it's going to be better. Let's see, tools, view, slideshow. Well, I'm not completely happy here because I lost this. Now, success. I have it. Okay, now strips has been studied for several years, and you know that for whenever you have a language, you have to describe the syntax, but you have also to describe the semantics, right? So what is the effects of, if it's a programming language, of instructions? If it's an action language, it's going to be the actions. Okay, what is the effect of the actions?
Professore, sta cambiando le...
Sì, è fuori dal mio controllo, sta andando avanti da solo, ecco, adesso lo sistemiamo. Ok, questo abbiamo... Ok. So we can define as a set transition system, the system as a triple. We take this simple, simpler representation. where S is a finite set of state, A is a finite set of action, and gamma from states to action into states is the transition function, okay? And of course, this will be specified through the action schema. Okay, so a planning problem, for a planning problem, we have to provide a specification of the action, which will be called problem domain, and then the specification of the initial state and of the goals. Okay, with these three elements that are the same for every problem. These are things that we have already mentioned. So me avoid to repeat. Here is an example of a plan for our supermarket agent. Go to supermarket, buy milk, buy bananas, go to the hardware store, buy the drill, and go home. Eventually, with a short plan, the agent will be successful. Well, of course, this is not a difficult plan to find in general, but it's going to be difficult in a situation where the number of choices for the agent at each step is not is very large, as the number of items in a supermarket or as number of locations where they sell things in this example. Here is another example, which is about transporting cargoes from one airport to another airport. So in order to understand the problem, we need to look at which are the actions available. So first we have an action load, which is intended to model the loading of a cargo into an airplane. So what are the preconditions of the action load? Well, we have to have the cargo and the plane have to be at the same airport. So the first two fluents, this is taken from the book, and you see that instead of the commas, you have the conjunction sign, okay? But you should read them as commas here. It's the same thing, actually. And the parameter A is unknown, is a parameter, but it's the same both for the fluent at, where the first parameter is a C, a cargo, and for the second fluent at, where the parameter P will be instantiated to a plane, okay? And then X must be a cargo, P must be a plane, and A must be an airport. And what's going to be the effect? And this is true essentially for every action where there is a change of the state of one object that changes the position. If we model the position with at, we have to say that the at, the effect is that the cargo will be in the plane. Therefore, we are going to have in C plane P. And then it's no longer on the ground of the airport. So not at CA. Now this may sound a little bit strange because it's still in the airport, even though it's in the airplane. So here we are distinguishing the fact that when we say at for the cargo, in airport, we really mean that it's at the airport, but it's not in the plane yet. Okay? Because this is maybe questionable, but this is the way we're representing the problem. So it's our choice. Okay? We could have used, of course, other predicates for the same problem, other fluents. Then we have the action unload, which is the symmetrical. Of course, in this case, the cargo must be in the plane, And once it's downloaded, it will be at the airport where the plane is. And then we have the action fly, which models the fact that airplanes can fly from an airport to another airport. So in particular, in this case, you see that the effect is that the airplane is no longer at the airport, departure airport, but it's got at the destination airport, okay? So we have to specify that it's no longer at the origin airport, because otherwise the representation will become inconsistent, because of course, we know that an airplane can only be in one airport, cannot be at the same time in two airports, different airports, the same airplane, okay? And we have to make sure that we keep this consistency when we specify the effects of the actions. Now, around the year 2000, the Strips language, which was given many different syntactical forms, was defined into a standard, which is called PDDL, Planning Domain Description Language, which has become a standard since then. In many ways, it generalizes strips, even though we are considering only the basic strips. And how does it look? Here is another problem. Here, this is the syntax. We'll see later. Let me first give you another problem and describe the actions of this problem. And then we will see the same problem formalized in PDDL, okay? Just to be patient for a couple of slides. So the blocks world has been the subject of several papers. It's one of the toy worlds, but we will see towards the end of the class that even in this toy world, we can realize that certain planning algorithms not always find the optimal solution. And this is what is called here a Sussman anomaly. It's the one researcher who pointed it out in a very successful and cited paper. It showed this unexpected behavior of the current planners at the time. Anyways, here we have two actions. One action is the action that puts a block on top of another block. And the other action is that puts a block on the table, okay? Removes, if you want, the top block from a tower and puts it on the table. So we have preconditions. Of course, in order to move a block, it should be clear both the block that we are moving and the place where the block where we are positioning the block that we are moving. So we have to have clear X and clear Y. And then we have as an effect that the on relation will be deleted, the clear relation of the destination will be also deleted, and we're going to have a clear block on top, let's say, of the tower, okay? Now, if you see the initial state and final state, it's very easy to get to a plan to reach the goal, right? Because we have to move C on the table, we have to put B on top of C, and we have to put A on top of C, okay? Here you will see the action formalization in the language that we have been using so far, okay? Sets of fluents, positive and negative, in the precondition and effects. And the book claims that this is the PDDL language. But in fact, even though it's just a syntactic sugar, as they say, here is the actual syntax of PDDL. You may notice the notation is Lisp-like, historical reasons. Lisp, an older professor of this department, to whom our laboratory is entitled, used to say that Lisp is the language with lots of parentheses. And here you see some of these parentheses. First, we have to define a domain. And as I mentioned, the definition of the domain amounts to defining the actions. And in fact, besides some declarations, so to speak, telling which are the predicates in particular, then we have two action definitions. And in the action definitions, we have three elements: parameters, effect, and precondition. Okay? And each of them, even though the expression is a parenthesized expression, but we can easily detect, for example, on B1, B2, where B1 and B2 are variables, and in fact, all the variables are denoted by an initial question mark. Okay? So a syntax, right? It should be used nowadays to multiple syntactic forms. Should be no problem. By the way, while for the search exercises, you do not have any possibility to check them, for planning, you can download a planner called FF, which is extremely easy to install. And then you provide you write two files. One is the domain file, and another one is the problem file that we're going to see in a second. And then you can run the planner and you get the plan. And I do invite you to do this, because having some sort of confirmation that the model that we have defined actually achieves the desired plan. Usually the plan that will be asked, that we are looking for, think about the plan on the Bloxworld. It's rather intuitive, right? It's no big deal. The point is to have a formal characterization of the action such that we get exactly that plan from our formalization. Remember that our goal is to learn how to model problems. And therefore, it's the model that counts more than the plan. Okay? Questions? No questions. Well, there is a question which says, if we look at the preconditions as hypothesis and effects as thesis, isn't the strips notation similar to Prolog language? Well, the similarity is rather vague, I would say, because in Prolog we essentially have implications, and we have at this point not even considered the logic, and even when we will consider the logic, it's not just a plain implication. So there is something true in what you say, but it's not a direct correspondence for sure. Okay, more questions at this point. I hope you enjoy the syntax of PDDL. And here is the problem definition. We have a reference to the domain. We have to mention the objects. We have to specify the initial state, and we have to specify the goal state. In this case, since there are no other objects, well, actually there is also The table, that's okay. In this case, we only have one goal. But we could have had a goal which is simply on BC, right? If we say on BC only, is this just one state or does it denote multiple states? This, I think, is an important remark because it tells you that both the preconditions and they have also variables, but in particular the goals that eventually have instances. If we say simply on BC, we're not saying anything about A. So there are a number of configurations where A is on top of BC, where A is on the table, where A is below C. They will all correspond to states that are goals in that case. Okay, so when we specify a goal, we're not typically not talking about one single state. We may be talking about multiple states. Okay? And this is just because in the goal, we have a partial specification of the state. Okay, we're not using the closed word assumption in the goal representation. Okay? Okay. Now we're going to look at the algorithms, the planning techniques. So we have three different models that we will explore. Today we will talk about planning in the state space. And then we're going to have next week a look at two other ways of approaching the problem, which are planning in the plan space or searching in the plan space and hierarchical planning. By the way, there is a course in the second year which is called Planning and Reasoning, where the algorithmic aspects of planning will be addressed in much detail. Of course, in this course, we will be talking, for example, about natural language, we'll be talking about other reasoning techniques, but there are other courses where these notions will be developed further. So, it's easy to characterize a planning problem as a search problem, or better, to use a search algorithm to solve a planning problem. Very simple. We have the initial state. We have the actions that corresponds to state transitions in the state space. And that's it. We can use all the algorithms that we have defined, except that we don't have any heuristics at the moment. And if we assume that all actions have the same cost, then we have a simple model with the unitary cost for each action. And which are the operators? Well, at each step, depending on the action specification, there will be some actions that are applicable and other actions that are not applicable. This is not very different from the modeling that you have seen for, except that the conditions for applicability are only determined by the preconditions in the actions and not by conditions that are different for every algorithm. I'm repeating this concept over and over because it's the most important one. Is the motivation why we need the structured models or factored models. Now, we have two, if we look at the reasoning in planning, we have essentially plan satisfiability, namely finding a plan that from the initial state allows to reach the goal, or a bounded version of this problem, which is find a plan of length k. Okay, so that's the bounded version. From a complexity standpoint, both plan SAT and bounded plan SAT, they are in P space. This is worse than NP that we have seen earlier, for example, for constraint satisfaction. Okay, it's a higher class of complexity. If we simplify the problem, and we can do it by, for example, restricting the language, like disallowing negative effects, then we get problems that are NP hard. So easier to solve than P space problems. And finally, if we disallow negative effects in negative effects and negative preconditions, so we completely remove the negation from the action specification, then we have a polynomial problem. Of course, we will not be able to model certain problems with all these restrictions in the language. Now, how do we search? Okay, having said what is the complexity? Well, in this particular case, we can search forward and backward. Guess what? Not a surprise. We have already learned about backward search, even though for search, it's more related to the possibility that actions can be reversed. Okay, namely, we can go from the effects back to the precondition in using the terminology of planning. But in fact, the action specification is such that this can be done. Period. Of course, we need to also figure out which are the heuristics for solving this problem efficiently. Okay, let's move on. Let's start about forward planning, which is starting from the initial state and then checking which actions are applicable in the initial state, and then creating the successor states and explore them. Now, this formula is repeating what is the state obtained by execution of an action. Is the state, the current state, without the delete actions plus the add actions, okay? Where minus and plus are to be interpreted in set theoretic terms, okay? In fact, we have this exactly the same, like this, we have exactly the same problem that I pointed out for search in general. There is the same blowout, because we have a compact representation because we have variables. So from the point of view of the problem specification, we have a compact representation. But then we have to create all the instances in order to generate a plan. And again, we have an explosion. So that cannot really work well. So for a long time, planning was mainly done from the goal back to the initial state in reverse order, so to speak. The process is called regression. We have seen that actions are invertible. We have to say something more about this, but in fact they are invertible because the goal representation is a set of states. It's not a single state. So we have to do a little, an additional specification on that. On the other hand, starting from the goal has the advantage that we understand where we want to go, and we try to build only the portion of the search space which is focused on achieving that goal. And that's why for a long time, this was the preferred way of planning. So we have a goal. I have already mentioned that, and we have discussed that the goal is done by several fluents, positive or negative. And this may represent a set of states, but we can simply say, well, if we have a state where any of these fluent is true, then we are fine, we have attained the goal. So what can we do? We can reverse the actions that will make the positive fluents in the goal true, and the actions that make the negative fluents that are explicitly present in the goal false. Okay? So we have a restricted set of actions that can actually do that. So for example, if we want to buy something and the goal is to have something, we can reverse this and from the object figure out, from have, we can figure out the preconditions of to be on a place where this particular item is being sold. So that's the relevant actions are those that achieve some of the fluents in the goal, or at a later stage, actions that achieve some of the preconditions that have been introduced in order to achieve the goal. So we go backwards. Whenever we solve something in the goal, we have new preconditions to be solved. And this process goes back until we eventually get to the initial state. However, there is another little, not so little maybe, thing to consider, which is the fact that maybe one action is going to achieve one of the fluents in the goal, but at the same time is going to delete another fluence in the goal. So this action will not be a good choice for our reverse project, because it is true that we'll achieve one or more goals, more fluents in the goal, but at the same time, it removes one of the goal, one of the fluents in the goal. Therefore, cannot be the last action in the plan. Okay, so we consider relevant actions and consistent actions, where consistent means exactly that they not destroy any of the fluents that are in the goal or in one of the current preconditions. And based on this assumption, we can do the process. And again, in this little formula at the bottom, you can see that whenever we are reversing an action, we take the state as represented, the current state of the process, initially will be the goal. And then from this, we remove the actions that have been added by the chosen action. The fluents that have been added by the chosen action, and we introduce the preconditions. Okay, we add the preconditions. So we apply the schema in the reverse order. And this is a process that is going to work and work effectively. It's important to notice that in this regression, in the example that I just made, whenever we regress, so we move from have bananas, we apply in the reverse direction buy, we are going to add two preconditions, which are sells P bananas and at P. So that P could be the supermarket, could be the hardware store, could be anything. It's a variable. Now, we could instantiate the variable at this stage, but there is a general principle that we will see also again in a much deeper way in logic, that you should never instantiate the variable unless this is strictly necessary. Okay, so if in one of these steps we get a variable, we have to keep that variable. Heuristics. You look tired. What time is it? 3:20. So cheer up, we are almost finished. We are close to the break. Students at home, how are you? Drinking wine or something? No answer, so maybe they're really drinking wine. Just water, vodka, yes, we are alive. Okay. Thank you. It's reassuring now and then to understand that you are still there, some of you. Okay, so as I mentioned, we are close to with the last slides, and we have to talk about the heuristics. After all, it's the last slides, but it's the important thing. I have to convince you that through heuristics, planning can be very effective. And in fact, this is something that was realized to a large extent around 2000. There is a competition that they have started, the researchers have started, about the fastest planner. So they provide a set of planning problems, and the fastest planner is the one that solves them in the shortest amount of time. And before 1998, everything about was backwards planners or regression planners, better. And in that particular circumstance, they came up with a forward planner, which was far better than the regression planners. Why? Because they had identified one particular heuristics that worked very, very well. And let's see what they are. There are two possibilities. One of them is relaxing the problem. We have seen this, right? In order to find a heuristic function, we can take the problem and try to find a shortcut to do the solution. And this will be in heuristics and will be also admissible because it will be typically an underestimation of the actual cost. Okay. Now, here we can reason on the shape of the action schema in particular. So we have two options. We can remove the preconditions completely. If we remove the precondition, every action is applicable in every state. And therefore we can add all the effects of the actions without any restriction. This sounds fine, except that this is still an instance of a difficult problem, which is the set covering, especially if we want to find the minimal set of actions that is needed. But in fact, we can approximate and we can find the solution fast. But we have to be careful when we look at the potential heuristics that this does not, that this is admissible, okay? Does not overestimate the cost, okay? So one of them is removing the preconditions, and the other one, which is the symmetrical, remove the negated effect or empty delete list. it's also called. And actually this empty delete list was the heuristics which was used in the first appearance of fast forward. So they compute the heuristics. In fact, they compute a plan for reaching the goal in this simplified setting and take the number of steps as a heuristic value and choose then choose the move, the action corresponding to that plan. How many steps are needed? They look at how many steps are needed, and the best solution is going to be the one that is chosen. Again, also in the case of empty delete list, we may have we have to solve an optimal, find an optimal, which may require exponential time, NP, but again, an approximate solution works very well as to provide a heuristic. Well, the admissibility is a condition that it's good to have because it allows to state completeness, but if not, may still be worth using, because in the end it will provide a good service, even though there are cases where it may not be so useful. Okay, so this is one possibility. Oh, notice that there is another possibility here, which is instead of removing the negative preconditions, it is possible to remove some of the preconditions. This is how one could formalize the action of the 8 puzzle, where we have an action slide which moves one tile from location S1 to location S2, okay? Now, this says that in the precondition, the tile T must be in location S1, T must be a tile, S2 must be blank, and S1 and S2 have to be adjacent. Okay, that's the precondition. In this case, the move can be done. And it's, I think it reads quite easily and straightforward. Now, what happens if we remove blank? Oops, I made. Okay. What happens if we remove S2 blank? We can move in any location, in any adjacent location, without any restriction. So this corresponds to the heuristics that we found by considering the Manhattan distance without any tile in the path. And similarly, if we remove blank S2 and adjacent, then we have the other heuristics, the weaker one, where we could jump in any location arbitrarily. So what is nice here is that from the problem formulation, we can remove the preconditions and find good heuristics. Okay, so in some cases, this is also something that can be useful in order to get a good heuristic. But this is not the typical case, because this has to do with the reasoning, again, understanding the details of how the solution can be found to some extent. Even though it's purely syntactical. And another possibility is to relax the problem. And one typical way of doing it is to consider the sub-goal independence. It's like problem separation that we have seen in constraint satisfaction. right? If we have a goal which is achieved, for example, on AB and on AC and on BC, we consider on AB separate from on BC, and you solve the problem just for that, find the plan just for that problem. Then you have n costs and n values, and you can take the maximum or you can sum. Are both the choices admissible? Well, if you take the max, yes, because you have you have to take at least as many moves as there are in solving one of the goals. But what about taking the sum? Last year, some students were able to answer this question. I don't understand why this year nobody. Why? The max is admissible, the sum is not granted to still underestimate. Why? You have to tell me why. It's clear that, in this case, it was not admissible, but I want to understand why. Any clue? Why the sum can be an overestimation? After all, they have all to be reached.
Forse non si considera che quando si raggiunge un goal, anche l'altro contemporaneamente viene in parte, cioè ci si avvicina.
Okay, I translate in English, but the answer is correct. In fact, it is possible that while solving one goal, you also work for another goal and maybe solve another goal at the same time, and this is not considered. So when you sum up, you can eventually come up with a number which is worse if you sum than the actual cost. Okay, so that was a good answer. In fact, this seems to be not generally the case, so it may be more an exception. And therefore, it's often used also the sum because it's not admissible, but it's a much better approximation, and the admissibility condition is satisfied in most cases. Now, there would be a lot to say about heuristics. In particular, you find a chapter in a section in the book which is about a way of finding heuristics, a technique for finding heuristics called graph plan. If you are interested, you can read. Otherwise, you will learn about graph plan in course planning and reasoning. Okay. Oops, again. Grr. Okay. Now, last thing. We are on this problem, right? We have these two actions. We want to solve with the planning, backward planning. This is a little bit of history. I want to explain what is the Sussman anomaly. Well, the algorithm that was used at the time was based on a stack. So the goals or the fluents in the goal were put in a stack, and then they were extracted one after the other. And for every goal, if this would generate other conditions to be satisfied, they would be put on the stack again. Okay? And once one goal, therefore, stack means exploration depth first, which was first solve the first goal. And once that is solved, then solve the second goal. Okay? Now, let's look here what happens with this problem. Here is the formulation. Our goal is on AB and on BC. We want to have a tower, ABC, with A on the top, right? So we have these two sub-goals. This is how they're called. If we start with goal on AB, we can solve this by putting C on the table and then placing A on B. Okay? This achieves the first goal. But now if we want to achieve the second goal, then we have to remove A from the position where we had just put, and then we can put B on C. And at this point, eventually, we discover that the first sub-goal is no longer true, and then we solve the first sub-goal by putting A on top of the tower. Okay? So what happens here is that when we solve the second goal, we destroy the first goal, and we have to rebuild. We still find a plan. But it's not the plan that I suggested earlier. Now one can think, well, that's okay. Let's first put on BC so that if we have a smart ordering of the goals, then we can find the desired plan. This is what happens if you start from goal on BC. This is achieved simply by putting B on top of C. Remember the configuration? Okay, here we put B on top of C. Now, this achieves the goal on BC. And at this point, we need to solve on AB. But in fact, again, in order to solve on AB, we have to destroy the first goal. In fact, we put on the table B, we put on the table C, and in the end, we do the on AB. If we do the first goal, now we put on AB and we achieve the first goal. But we lose the second, and we are back in the situation that we have described earlier. So we will eventually find the goal, but it will not be the desired plan that everyone intuitively had in mind. So that's why this was called Sussman anomaly, which was showing that this essentially depth first, start considering the goal in any order would not lead to the optimal solution, the desired solution. And this was called the Sussman anomaly, and they changed the way they were thinking about planning at that time. Okay, I think it's time to have a little break. I will stop the recording now at this point, because in the second part with the exercises, there will be no recording, so you can say all sorts of things without being recorded, okay?